69. Let me copy it. So a of t, which is the acceleration, the second derivative, sine t minus cosine t. S of 0 is 0. S of pi is 0. Perfect. Okay. So notice that this time we do not have any condition for the derivative. Both of them refer to the distance. Okay. So from here, we will continue with the velocity. Which function prime is sine t? You will tell me negative cosine t, minus which function prime is cosine t, that is sine t, plus a constant, you can call it c1. I don't have any restriction or condition or initial condition, so I will have to continue with the distance. Which function prime is cosine t with minus in front, so that's negative sine t. Which function prime is negative sine t, which I know is cosine t, plus c1t, because this derivative, when I differentiate this, I get c1. When I differentiate this, I get negative sine t. When I differentiate this, I get negative cosine t, plus c2. So this is it for the most general antiderivative, or the entire family of functions whose second derivative is this. Now, the reason I have two conditions is that one will help us determine C1 and the other one will help us determine C2. There is nothing wrong. If you'd like to stick with C and D, that's fine. C1, C2 is fine too, whatever you want to denote them. It doesn't matter. So S of 0 equals 0. 0 equals, this is 0, but this is 1. But this is 0 plus C2. From here, we know that C2 is negative 1. So I will rewrite S of t equals negative sine t plus cosine t plus C1t, and then minus 1. Finally, I will be using that S of pi is 0. Okay, so 0 equals sine pi, we know is 0. Cosine pi, we know it's negative 1. C1 times a pi will be plus pi. You know what I mean. C1 times pi. Yes, pi C1. And minus 1. So I move these two to the other side. 2 equals pi C1. So C1 equals 2 over pi. Plug it in for C1, and this is it. That's the final form. Negative sine t plus cosine t plus 2 over pi t minus 1. And this is it. I know I sound like a broken record, but that's okay. I will always beg my students to redo the problems we do in class. It will give you tremendous understanding and tremendous confidence. That's the first step you should always do. I always say it, and I'm hoping. Okay. Any questions? I'm sorry, I didn't mean to take it too fast.
Yeah, how did we get C2? Oh, okay.
So S of 0 is 0, 0. Sine 0 is 0. Cosine 0 is 1. C1 times 0 is 0 plus C2. And we move. Then I have to put it in. And then I use the second condition as S of pi equals 0. So 0 here, 0 here, negative 1 here, pi times C1 and minus 1. I move the 2 to the other side and divide by pi. Is that okay?
Yeah, that's okay. I get it now.
Thank you. Other questions, anyone? Thank you, Isaac. Other questions? Okay. Chapter 5. I don't want to put the title yet, so I will have to start with some preliminaries. And here is number 1, preliminary. Let's look at something like 1 plus 2 plus 3 plus dot, 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 let's say 100. So this is basically a sum of terms. Sum of terms. There is a symbol that condenses this notation. And it's this. It's called sigma. It's the uppercase sigma that we know about, epsilon, delta, or sigma, right? We know sigma. But this is the uppercase sigma. It stands for summation, also called summation notation. It's the Greek letter S. It's the Greek letter S. S would be okay, but it doesn't have the great shape that the Greek letter S has. Because, why is this important? Why we use this notation is because something follows here at the bottom of this sigma notation, and something at the top, and also something in here. And this whole thing will replace what you see on the left-hand side. So first of all, it has to have an index. The index of the summation notation normally is I or J or K, but it doesn't really matter. Okay, so let's say I'm using I. From I equals 1 till I equals 100. This is the lower limit. Doesn't have anything to do with this with the limit operator. It's called the lower limit. And this is called the upper limit. Again, this has nothing to do with the limits from previous chapters. It's just called the lower limit and the upper limit. And from I, so you can say, wait a minute, how come that this notation replaces this? Let me explain how. When I is 1, I have the first term. Sigma notation says sum, so I have to put plus. When I is 2, then I have 2. Sigma notation again says plus. When I is 3, I put 3. Plus, dot, dot, dot. Exactly 3 dots, not 4, not 2, not 1. Exactly 3. Plus the last one. So why do I need this in this chapter? You'll see. Okay, we're going to get there. I'm going to explain why we need it. But this is the sigma notation. And generic terms can look like this. AI. AI is the generic or general term. Same thing. The general term from I equals 1 through n. How does this translate? What is this? What does this represent? When I is 1, I have A1 plus A sub 1 if you want. When I is 2, I have A sub 2. The sigma notation says plus. When I is 3, I have A sub 3 plus dot, dot, dot. Can anyone give us the last term of this summation?
M.
A sub n. Is this okay? Okay, now, of course, the summation notation comes with properties. Properties. Every time a symbol or something is invented, things follow immediately. And there are two major properties. The sum from I equals 1 through n from a sum of two general terms. Let's say AI plus BI or minus BI. Like before with the limits and derivatives and everything else. It's the sum of AI plus or minus the sum from BI. From I equals 1 through n, from I equals 1 through n. So the same thing we had when we differentiated, as an example, a function plus another function. We differentiated the first, plus we differentiated the second. Same idea. So the sum from AI plus BI is the same with the sum of AI plus the sum of BI. That's two properties in one, a sum or difference. And here there is one more. We're going to use this property. And there is one more. And here it is. Property 2. The sum of a constant times a general term. What do you think will happen? We've seen it with limits. We've seen it with derivatives. We are seeing it again with a sigma notation or summation notation. Anyone?
The sum of C times sum of A to sub I.
Right? C, the sum of AI from I equals 1 through n, right? Remember? So 3 times the function prime is 3 times the function prime. Same thing. If we had limit of 3 times the function when x approaches a, we had 3 times the limit of the function as x approaches a. So a constant, that's what I was always hoping, and I always try to instill this in my students' memory. Simplify and factor, always, right? So the constant goes outside if it's a factor. If it's plus, no. But if it's a factor, in other words, multiplied, it will always go in front. Okay, so now one more preliminary. There are 4 identities. 4 identities. Here they are. The sum of 1 from I equals 1 through n. Any guess? Any guess? Okay, let's look at an example. The sum from I equals 1 to 7 of 1. When I is 1, 1. When I is 2, 1. When I is 3, 1. When I is 4, 1. When I is 5, 1. When I is 6, 1. When I is 7, 1. How much is this?
Seven.
That's it. A wild guess? Very good. Yes, my n and my m kind of look the same. Sorry about that. So it's the upper limit. Good. On the other two, we cannot guess. So the sum of I, when I equals 1 through n, I will give you the formula. n plus 1 divided by 2. If you say how, I can show you using mathematical induction. With mathematical induction, we can prove B, C, and D. The first one doesn't have to. It's too easy. The sum from I squared, from I equals 1 through n. This one is the most cumbersome to remember. n plus 1, 2n plus 1 over 6. n plus 1, 2n plus 1 over 6. And the last one is the sum of I cubed, from I equals 1 to n. Same thing, but squared. So that's easy. n plus 1 divided by 2. So let me just show you again what this represents before we put the final answer in. Just to make sure that this is clear how it's done. Let's say I'm just going to show the last one. So the sum from I equals 1 through n from I cubed is, when I is 1, the sum says plus. When I is 2, the sum says plus. when I is 3, when I is 4, dot, 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 when I is n. This sum is given by this formula, depending on n. What about c? C will be the same. I squared plus 1 squared plus 2 squared plus 3 squared plus 4 squared plus dot, 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 plus n squared. So now, is there a way of calculating this quickly? So for example, if you ask me to calculate the sum from I equals 1 to 1,000 of I have no problem. I know the formula n plus 1 over 2, where n is 100. 100 times 101 divided by 2, I'll simplify, and I get 5050, done. I'm not going to sit here and add from 1 to 100, because we know the formula. Let me show you with these new calculators. Not all calculators have this feature, however. Okay, this was my statistical inference this afternoon with my students. Okay, so in math, go up. It has the summation notation right here. It's 0. And we had x. It doesn't have I, j, k, so you have to use x to 100 from x. And when I click enter, it has to give me 5050. So there are all sorts of different situations in which we want to calculate this. If you don't have this kind of calculator, stay at the end and I'll show you with, you have to use the catalog sum of the sequence. Okay, so we can do that. Okay, so now you can say enough of it. I got the idea. Let's also look at one more example. Let me just make one up quickly. Let's say that for the sum from I equals, it doesn't have to start at 1. I'm just going to change it just for the sake of the argument. From I equals 4 to 7, from 3i squared plus 2i minus 4. I have no idea what this is. We're going to calculate it with a calculator in a minute. But when I is 4, I have 3 times 4 squared plus 2 times 4 minus 4, plus. When I is 5, I have 3 times 5 squared plus 2 times 5 minus 4, plus. When I is 6, 3 times 6 squared plus 2 times 6 minus 4, plus. When I is 7, 3 times 7 squared plus 2 times 7 minus 4. These are the 4 terms. When I is 4, plus. When I is 5, plus. When I is 6, plus. When I is 7. I have to plug in everywhere. And how do I do this with a graphing calculator? Just punch it in. Just recall what you just had. And I'm just going to change this at the top to 7. Where's my 7? And
Can you change your screen?
oh, I didn't share? What am I doing? Sorry. Let me start from scratch. Sorry. So go to math, go to 0. It will bring this. So I, which is x in this case, from 4, x equals 4, upper limit. I just made up an example. Now, sometimes this calculator may require to put in parentheses again what you have inside. So I don't know when it does require that. When it doesn't, I prefer putting it in parentheses. Now, if it says it's an error, then I have to remove the parentheses. Sometimes it's fidgety for some reason. I don't know. Some calculators require double parentheses, others don't. So I can't, okay, so it deleted those. So this one, at least on the computer, does not. So I cannot verify this because I did not calculate by hand. So the answer is 406. Okay. So I didn't show you. There was a chat for me. Oh, okay. So is everything okay? So back to why are we doing this? And now we're starting chapter 5. This was just preliminaries and very important preliminaries, actually. Okay, so areas under graphs. This is another application of anti-differentiation. Application of anti-differentiation. However, before I show you the shortcut, which I cannot right now, let's talk about just areas on the graphs. And you'll see where I will connect the dots for you, of course. Okay, so let's take a very simple example. Let's say f of x equals x squared, and an interval, let's say, between 0 and 2. When I graph this function on the interval 0 to 2, 1, 2, 2 squared, 1, 2, 3, 4. Okay, here's the graph. This is the graph of x squared between 0 and 2. And this is the area under the graph. The question is why I'm looking at the area under the graph. Please, I'll explain what I do. Well, I'll explain in detail why. The explanation is here already. The explanation is already in here, but I'll explain more, and I'll explain with other examples also. Okay. Okay, so we want to determine this area. We don't have an exact way. We do not have the exact way just yet. We do not. We will. By the end of this chapter, you're going to be masters of determining areas on the graphs. But right now, we don't have this exact way. Okay, so let's also suppose that we are asked to use 4, lowercase n, 4 subintervals. What does that mean? Of equal width. Of equal width. What does it mean? So let's take a look at the interval 0 to 2, this interval right here. So I'm dividing it into 4 equal pieces. The width of each piece of each subinterval is delta x, uppercase delta x, which is 2 minus 0. So the interval in general will be a comma b, right? B minus a divided by n. B minus a divided by n. Of course, in our case, in 0 to 2 and 4 subintervals, for this case is 2 minus 0 divided by 4, which is 2 over 4, which is 1/2. So the width of this interval is 1/2, the width of this interval is 1/2, the width of this interval 1/2, and so on and so forth. Good. So we are told, find, you cannot, approximate, I should have said, approximate the area under the graph using 4 subintervals of equal length or equal width, and that is 1/2. So I divvy up here now the interval 0 to 2 into 4 equal subintervals. We have several ways, but in this Calc 1, we are only looking at 3 possibilities. Using leftmost point. I'll explain what that means. Using the rightmost point or midpoint. Using. Okay. So either the leftmost point or the rightmost point or the midpoint. We're going to, for this example, we're going to use all 3. Okay, so we're going to repeat the process of approximating the area under that graph using the leftmost point, rightmost point, midpoint. What does the leftmost point mean? Well, I'm going to create rectangles. So looking at this first subinterval, using the leftmost point, there is no height here. So the area of the first rectangle will be base times height. I'm using the leftmost point, but f of 0 is 0. I'm moving on to the next subinterval, base times height. And this is a rectangle. The next one, for the third subinterval, this is the height. I'm using a rectangle. This will be the area of the next. And the last one, because I can only use 4, is this one, where the height is rectangle. So then the area approximated using 4 subintervals and the leftmost point will be base times height plus base times height plus base times height plus base times height. So this is at 1/2, this is at 1, and this is at 3/2. So the area with left 4 approximately, since the base is the same, I will put 1/2 in front and then parentheses or brackets, f of 0 plus f of 1/2 plus f of 1 plus f of 3/2. F of 0 plus f of 1/2 plus f of 1 plus f of 3/2. We're going to calculate this right now, but question, do you think that the number we get is an underestimate or an overestimate of the actual area, of the exact area? I know it's a silly question, but I just want to... Yes, Brian, sorry.
Underestimate.
Well, of course. How come? Because look at these empties. These are missing. So I will get an approximation that will be an underestimation of the exact area. Okay. So I have 1/2 in front, f of 0 is 0, f of 1/2, I plug it in the function, so it's 1/4, f of 1 is 1, and f of 3/2 is 9/4. Let's see what we get. So this is 10/4, so 1/2 times 10/4 is 5/2, 5/2 plus 1 is 7/2. So this is 7/4. I used, to approximate this area, I used 4 subintervals and I used the leftmost point, the height based on the leftmost point of each subinterval. Okay, I will graph again. I cannot put it on the same. I was thinking to enlarge it or not, but I think we all see this. Still 4 subintervals, but now careful, which color will be best? So base times height, base times height, base times height, base times height. So the area with right 4 is approximately still 1/2, but this time this is 1/2, this is 1, this is 3/2, and this is 2. F of 1/2, base times height, base times height, f of 1 plus base times height, oops, f of 3/2 plus f of 2. Okay. So let's see what this is. By the way, is this going to be an underestimation or an overestimation of the exact area?
Over.
Yes. How come? Because we have these pieces. They're not under. right? So I have 1/2, then I have 1/4 and plus 1 plus 9/4 and plus 4. Okay, let's see what we get this time. 1/2, because I'm hoping that by the end of the day today, we're going to be able to determine this exactly. So we can always go back. If we have time, I hope so. So 10 divided by 4 is still 5/2, and this is now plus 5. So 10, right, 15. So 1/2 times 15 over 2, 15 over 4. Okay, last one. And for this one, I have to enlarge it. So I'm just going to graph something, okay? Without, I mean, what I meant was I'm graphing the same function, but without, because if this is 2, this would be 4. So, but you know what I mean. Okay, so now we'll talk about the midpoint with 4 subintervals. Here's the midpoint, here's the height, here's the rectangle. Midpoint, height, here's the rectangle at the height. Midpoint, height, here's the rectangle. Midpoint, height, and here's the rectangle. So the area with M4. Now, if this, now we have to determine these points, right? Because this is exactly the same, so it's 1/2, but it's f at this point plus f at this point plus f at this point, this height, this height, this height, and this height. So if this is half, this is 0.25, so this is 1/4, right? 1/4 plus 1/4 plus 1/4, 3/4, plus another 5/4, plus 2 more, 7/4. So f of 1/4 plus f of 3/4 plus f of 5/4 plus f of 7/4. And this will be 1/2, 1 over 16, 9 over 16, 25 over 16, 49 over 16. So what do I have here? So it's 10, so this is 59 and 25. I think I have 84. So I have 84 divided by 32. And I can simplify, right? If I simplify by 4, I get 21 over 8. Now, in this situation, 21 over 8 should be between the overestimation and the underestimation. But this is less important. There are other ways of determining, yes. We have the trapezoidal rule, we have the Simpson's rule, but that's for Calc 2. So we have other options. These are not the only 3. Okay. Now, what I am interested in